Hello students, so today we are going to discuss about heap tree and from heap tree we will perform heap sum. So before I get into the practical, let me discuss few basic concepts which are related to heap tree. So this example shows a complete binary tree. Already when unit number 2 was taken, in the trees we have seen there are many types of trees and complete binary tree is one of them where the filling of node always happens level wise, or else we can say that the nodes are always filled from left to right. So if we want to represent the binary tree using array, then there must not be empty spaces. Suppose if this tree I want to represent using an array representation, so this is the way how it will be stored in the array. So the root goes at index number 0, the next level element 2, 3, they will go at the index number 1, 2, and so on, like 4, 5, 6, 7, all of them are at the same level. So they go at the index 3, 4, 5, 6 accordingly. So now we know that there must not be any empty spaces in between so that it will be filled from left to right. If we look at these three diagrams, we know this is the tree in which the filling of nodes has happened from left to right. So yes, this is a complete binary tree. But if we consider this tree where we can see the root has two children node and this left child is not having any children further, so here the filling of node has not happened from left to right. Rather, this node has its own left child, but this is not from left to right direction. So this is not a complete binary tree. If I consider this example, the next example, here also the filling of node has not happened from left to right. So if it would have been from left to right, then this node was expected to have a left child, but it is not so. That's why this is also not the example of complete binary tree. So we need to remember about heap tree is that in heap tree, filling of node always happens from the leftmost position. Now, if we talk about the height of the tree is log n, because we know unless we fill nodes in one level, we won't be able to move to the next level. So that's why we know that the height of this complete binary tree is log n. One more thing is about the position of left and right child. The position of left and right child. Now, if I consider suppose the root is stored at index I, then it is for sure that its left child is at 2 into I plus 1 position and the right child will be at 2 into I plus 2 index position in the array. So formulas are also needed because many times we have to find out the smallest one or the largest one than the root. And in that case, we must know the position of left child and right child in the heap tree. So please remember that if parent is situated at index I, then its left child will be at position 2 into I plus 1 and the right child will be at position 2 into I plus 2. Now, based on this definition, there are two types of heaps, max heap and mean heap. So in this max heap, we can observe the value of root is greater than its left and right child. Same thing here also you can see that the value of left and right child is smaller than the root. So root is greater. Here also 20 is greater than 8 and 16. So a heap tree in which value of root is greater than its children is called as max heap. In case of mean heap, what happens? The value of root is going to be smaller than its left child and right child. So here also we can observe that value 10 is smaller than 30 and 20. Here also value 30 is smaller than 35 and 40 and so on in this subtree as well. So here root is smaller than all other descendants. Here root is greater than all other descendants. And yes, corresponding array representation for this max heap and mean heap is shown over here in the figure. Now, let us have a glance at how insertion operation happens in the heap tree. So this is called as max heap, where you can see the value of root is greater than its children and the root is greater than all descendant nodes in a tree. So if I want to if I want to represent this tree in the form of array representation, so this is how it will look like. So in array, the nodes are kept level wise. So index 0, level 0, that is 50. Then the next level 1, elements 30 and 20 will be stored. Then the next level 15, 10, 8 and 16 will be stored, and so on. Now, if at all I want to insert one element in this heap tree, where it will be inserted? So already we have seen the property of heap tree that nodes are inserted from leftmost position to the right. So left to right. So it simply means that if I represent this heap tree in this array representation format, the new element which I want to add in a tree, it must go at the last index in the array. That is index number 8 here in our case, right? So now if I put 60 over here, and as this is a case of max heap, we come to know that in case of max heap, what happens? Value of root is greater than its children. But now if I look at the position of 60, its parent node is 15 and 15 is smaller than 60, which is violating the property of max heap, right? So here I need to swap this 60 with 15. So now 60 would come up, but again 60's parent is 30. 60 is greater than 30. So even 30 and 60 will be swapped. And then I will have 60 here and 50 here. But again, 60 is the largest element in a tree that should move up to the root level. And so here at the end, what I will get at the top is 60, and my heap tree will be rearranged in this way. So this is my original tree, and here we can see that after adding 60 into the tree, how the tree is hippified or how my tree is repaired, right? So how much amount of time is taken for hippification process? So number of comparisons to be performed, they are depending on what? They are depending on level. And you know, level is nothing but height of the tree, right? So height of the complete binary tree is log n to the base 2. So we know that height of the tree is log n to the base 2. Okay, so number of comparisons which will take place, they are depending on what? They are depending on the level. Okay, what is height of the tree? How many levels are there in a tree? So likewise, we need to decide, and hence the comparisons in heap sort, they are equal to big O of n log n. Considering that you have to insert n elements in the tree, heap tree, so the total number of comparisons will be equal to big O of n log n. So this is about the short theory or prerequisite related to heap tree. Because ultimately, if I want to perform heap sort, what should I know is about heap tree as a data structure. And now let us talk about deletion operation. So here I have considered the case of max heap. Now we know that if I consider this heap tree and if I want to perform delete operation, always whoever is there at the root will be deleted. And we know that in case of max heap, the root is expected to have largest value in a tree. So if I perform delete operation on this tree, then 50 will be deleted. Okay. And if I delete 50, then the next question immediately comes in our mind that who will take place of 50, that is root. So always remember that just like insertion happens at the end of array, similarly for deletion, the last element in the array will take place of the root. So we can see here, or we can see here also in the tree representation that 16 is the last element in a tree. So after performing delete operation, 16 will take place of 50. Okay, 16 will take place of 50. But after swapping the last value with the root node, not swapping, after replacing last value in place of root node, we have to still ensure that tree is a heap tree. That is, as we are following max heap, we have to ensure that tree still satisfies the properties of max heap. But in our case, it is not, because now at the root position, I have 16. 16 left is 30 and 16 right is 20. And max heap suggests that the largest number should be there at the root. Okay, so here 30 should be there at the root. So I find out who is the largest element from the left and right child. So 30 is the largest element. So what will happen? 30 will be swapped with 16. So 16 would go down and 30 will come up as a root. Okay, so after performing this swapping, my tree becomes 30, 16, 20. Then the next level 15, 10 and 8. And this is the similar array representation. Okay, so what we have to remember in case of deletion, always the element which is present at the root position is deleted, and the last element in the array will take place of the number which is there at the root position. Okay, so you have to remember that how insertion happens in a heap tree. Insertion always happens at the end of the array. So while filling the heap tree, elements are or nodes are always filled from left to right. Okay, and in case of deletion, the node at root position is deleted, and then who will take place of the root node? Last element in the array will take place of root node. So this is about two primitive operations on the heap tree, that is insertion and deletion. Now, why heap sort is needed? Earlier, we have seen many types of sorting techniques. Some of them they were using recursion, some of them were non-recursive, but still there are some advantages of heap sort over others. So heap sort is fastest one. And the main thing about heap sort is it doesn't require any kind of recursion. Okay. And already we have discussed that number of comparisons in heap sort, they are based on height of the tree, that is log n to the base 2. And as we are inserting n numbers in the heap tree, the number of comparisons will be equal to big O of n log n. Okay. Now, what are the steps in heap sort? The very first step is we have to build a heap tree. Maybe you can prefer max heap or min heap or based on the condition whichever is given in the problem statement. And then we start performing delete operation. Now we know that whenever we perform delete operation, the value present at the root is deleted. So if it is max heap, the value at the root position will be deleted and it will be stored in other array. So whenever we delete element from the max heap, we get list in the descending order. But if we are deleting elements from the main heap, we will get list in the ascending order, the smallest one first and then the largest, and so on. Okay, so while performing heap sort, first step is we have to build a heap tree with given data, maybe main heap or max heap. And in second step, we have to delete the root node from that heap tree. And in third step, after deleting the root node from heap tree, we have to rebuild our heap, or this step is also called as heapification of the tree, or it is also called as repairing a heap tree. And then this step we have to repeat until the heap is empty. So when we delete all the elements of the heap tree, then we have to stop with this deletion operation. It means that all the nodes in a heap tree are deleted, and yes, we are there with sorted numbers in the descending order. Okay, so this is how heap sort is to be performed. Now for the demonstration purpose, I will just show you the title, like which we have to perform in the practical. Now what is the title? So title here is a dictionary stores